Well, welcome to the Explainer. Today, we're diving into one of the most elegant, most beautiful ideas in all of machine learning, the support vector machine. We're going to build a really deep, geometric intuition for how it works. And along the way, we'll uncover this brilliant trick it uses to solve problems that, at first glance, seem completely impossible. All right, let's just jump right in with a puzzle. Imagine you've got two groups of data, but one is totally encircled by the other, kind of like the yolk inside an egg. Now, the only tool you have is a model that can only draw straight lines. So how on earth can you separate them? It feels impossible, doesn't it? This is the core puzzle we're here to unravel. And look, this isn't just some abstract thought experiment, right? If you've ever actually worked with real-world data, you know this feeling. You build a simple, straightforward model, and it works great on the clean, textbook examples. But then you let it loose on reality, with all its noise, all its messy, nonlinear patterns, and the whole thing just falls apart. That's the frustration we're tackling today. To solve that circular puzzle, we first have to build our intuition from the ground up. So for a minute, let's forget about circles and messy data. Let's start in a much simpler world, one where our data can be separated cleanly by a nice straight line. The tool we're going to use for this is called a hyperplane. Now, I know that word sounds a little complex, but it's really just a general term for a decision boundary. If our data has two features, say height and weight, the hyperplane is just a 2D line. If we add a third feature, it becomes a flat 3D plane. So you can just think of it as the wall we're building to separate our two groups. Now, if you look at this data, you could draw, well, an infinite number of different lines that perfectly separate the blue dots from the green ones. A more basic classifier might just be happy picking any one of them. But an SVM is more ambitious. It's not searching for just any line that gets the job done. It is hunting for the single, best, most robust line, the one true hyperplane. So how does it define best? Well, the critical insight is this. The best boundary is the one that stays as far away from the data points of both classes as it possibly can. I want you to think of it like paving a road between two towns. You wouldn't want the road to just skim the edge of either town, right? No, you'd want to build the widest possible road right down the middle, maximizing that buffer zone on both sides. In SVM speak, that buffer is called the margin. And here's the really fascinating part. That widest road, its position isn't determined by all the data points. It's defined only by the points that are closest to it, the ones sitting right on the edge of the road. These are the support vectors. You can think of them as the most difficult, most ambiguous points to classify. And they alone support the entire structure of our hyperplane. You know, if we removed any of the other points, the line wouldn't move an inch. But if we move a support vector, the optimal line shifts right along with it. Okay, so that's a beautiful idea for clean, perfectly separable data. But we know the real world is, well, it's messy. So what do we do when the data points start to overlap and there's no single straight line that can get the job done perfectly? This is where we have to introduce a bit of flexibility. The hard margin SVM we've been talking about is a really strict rule follower. It allows zero misclassifications, period. But the soft margin SVM is much more pragmatic. It actually allows some points to be on the wrong side of the line, but it makes them pay a price. We introduce this penalty parameter, this C you see here, which basically controls that trade-off. A really high C means we're penalizing mistakes heavily, pushing the model to be stricter. A low C is more forgiving. It allows for a wider road, even if it means a few points end up on the wrong side. It's like a dial for tuning between being a perfectionist and being pragmatic. Now, with that idea in our back pocket, we can finally return to our original puzzle, that data arranged in a circle. The most intuitive solution, the one that probably jumps to your mind first, is to just give up on our straight line and try to draw a circle or some other kind of complex curvy boundary. And it seems logical, but it's a seductive misconception. It's a trap that leads us toward more complex models that often don't generalize very well. So instead of making our line more complicated to fit the data, the SVM uses a much more elegant, much more powerful idea. It asks a totally different question. What if we could change the data itself so that our simple straight line works again? The philosophy here is just, it's profound. Don't bend the line. Bend the space the data lives in.
Let's really see how this works. We start with our impossible to separate circular data, sitting there on a flat 2D sheet of paper. Then, we apply a mathematical transformation. I want you to imagine we just poke the center of the paper from underneath, pushing that inner circle of points up into a third dimension. All of a sudden, the data isn't tangled anymore. The green points are now floating above the blue points, and because of that, we can now do something that was impossible before. We can slide a simple, flat plane, our hyperplane, cleanly right between the two classes. We didn't draw a curve, we just looked at the data from a different dimension, a dimension where it became simple again.
This right here is the absolute magic of the support vector machine, and it's called the kernel trick. Now you might be thinking, okay, but projecting data into higher dimensions, that sounds computationally insane. And you'd be right, it should be. But here's the trick. It turns out that all of an SVM's calculations only depend on the dot product between points, which is really just a measure of their similarity. A kernel is a special kind of function that lets us calculate this dot product as if the points were in that higher dimension, but, and this is the key, without ever actually doing the transformation. It is a stunningly efficient mathematical shortcut. It's like getting a first-class ticket for the price of coach. So, this idea of bending space, it isn't just one move. It's an entire toolkit of possible transformations. So let's take a look at how we choose the right tool for the job. The specific type of transformation we use is decided by our choice of kernel function. The linear kernel is kind of the default. It does no transformation at all. It's our straight line. The polynomial kernel is fantastic for data that has, well, polynomial relationships. And then you've got the radial basis function, or RBF kernel. This one is often the go-to for really complex problems because it effectively maps the data into an infinite dimensional space. It's incredibly powerful and usually a great starting point when you're not sure about the structure of your data.
And this powerful, flexible approach is exactly what makes SVMs so effective across a huge range of really difficult problems, from classifying the incredibly complex patterns in images, to sorting through text documents, or finding hidden signals in high-dimensional genetic data, even recognizing the subtle variations in someone's handwriting. Pretty much anytime you have a complex classification problem where a simple straight line just won't cut it, an SVM with the right kernel is going to be a very, very strong contender.
Okay, we have covered a lot of ground, from building wide roads to literally bending the fabric of space. Let's distill all of this down into a few core ideas, a few mental models you can take away to think more clearly about these kinds of problems.
So, if you remember nothing else from our conversation today, remember these 3 ideas. First, an SVM doesn't just separate data, it finds the widest possible road, and that road is defined only by the toughest, most difficult points to classify. Second, when you're faced with tangled nonlinear data, resist that first impulse to draw a complicated line. The much more elegant solution is to reimagine the space itself. Don't bend the line, bend the space. And finally, the kernel trick is our superpower. It's the mathematical shortcut that gives us the power of high, even infinite dimensions without the crushing computational cost.
And what's so cool is that this illustrates that the kernel trick isn't just some gimmick specific to SVMs. It's a general-purpose, powerhouse concept in machine learning. And that leaves us with a final thought to chew on. If this one idea, changing the space, can turn a simple linear classifier into a nonlinear powerhouse, what other simple linear algorithms, things like PCA or linear discriminant analysis, could be completely transformed in the same way? What happens when you give them this same superpower? The possibilities are pretty fascinating to think about.